Hello to all my viewers. This is Dr. Dhaval Maheta, and today we'll understand how to run logistic regression analysis in STATA. Logistic regression analysis is a widely used statistical modeling technique applied when the dependent variable is binary or dichotomous, typically coded as 0 and 1. Unlike linear regression, which models a continuous outcome, logistic regression estimates the probability of an event occurring, example, success versus failure. That's a probability of success versus probability of failure, disease versus no disease, admitted versus not admitted. The central feature of the logistic regression is the logit transformation, where the natural logarithm of the odds of the dependent event, remember odds of the dependent event, is modeled as a linear combination of the predictor variables. The predictor variables are the independent variables. Key assumptions of the logistic regression: we start with the first one, binary or categorical dependent variable. The outcome variable should be binary. The values it can take is 0 or 1, success, failure, admitted, not admitted. Independence of observation: each observation should be independent of the others. Linearity of logit: continuous independent variables are assumed to have a linear relationship with the logit of the dependent variable. Absence of multicollinearity: independent variables should not be highly correlated with each other. No extreme outliers or influential points. Outliers or highly leveraged cases can unduly influence the model. Good model fit: the model must be validated for adequacy using the fit indices such as Hosmer-Lemezov test, pseudo R-square measures, Cox and Snell. Is a pseudo R-square measures, ROC curve, that is receiving operating characteristics curve, also known as the area under the curve. So let's understand the concept of logistic regression. For each value of x, so x can be a continuous also. In case of logistic regression, we want the values of y should take either 0 or 1. So 0 non-bias, 1 bias, 0 not admitted, 1 admitted, 0 no disease, 1 disease. Now, is it possible with the help of linear regression? Let's see it. See, we are having y is equal to 0, that is non-bias, and its points are there. See these blue dots. And y is equal to 1, the bias. These are the blue dots for that. Now, if we try to fit the linear regression into this, what will happen? There is a possibility that the values will go beyond y is equal to 1 and it will go below y is equal to 0. So the predicted dependent variable can go beyond the 0 and 1 limits. This we don't want. We want to confine that the y should take only the values 0 and 1. So this problem can be solved with the help of sigmoid function. So that's the reason we use logistic regression. Now in this case, the predicted dependent variable remains inside the range of 0 and 1. Logistic regression converts the output of the dependent variable to a binary outcome, 0 or 1, through the use of sigmoid function. The logistic function maps any real number z into a value between 0 and 1, which can be interpreted as probability p. To convert the probability p into a binary outcome 0 and 1, a threshold is applied. If p is greater than or equal to 0.5, predict the outcome as 1. If the probabilities are more than 0.5, predict the outcome as 1. And if the probabilities are less than 0.5, predict the outcome as 0. Logistic regression converts the output of the dependent variable to a binary outcome through the use of logistic function. Let's understand how it does it. Z is equal to beta 0, beta 1, x1, beta 2, x2 till beta and xn. So betas are the coefficients and x are the predictor variables. Logistic function is to convert this linear combination into a probability that ranges between 0 and 1. So for this we are using p is equal to 1 upon 1 plus e raised to minus z. We are using this equation because we want the values should be between 0 and 1 only. So now our logistic regression is p y is equal to 1. That is only for success we are computing the probabilities. equal to 1 upon 1 plus e raised to minus z. It's the same thing. Now we have substituted the value of z, which is this one. So the logistic function maps any real value number z into a value between 0 and 1, which can be interpreted as a probability. When z is large and positive, p approaches 1. See this one. This. And when z is large and negative, p approaches 0. When z is equal to 0, here, p is 0.5. Now, what are odds? And why is it necessary to understand in logistic regression? Let's see. An event can have only two possibilities, success or failure. Let's convert it into the probabilities. Probability of success and probability of failure. Odds is the odds of an outcome represent the ratio of the probability of the event happening to the probability of the event not happening. Probability of success divided by probability of failure. In the context of logistic regression, it helps to understand how likely an event, that is a success, is compared to a non-event, that is a failure. The formula for odds is equal to p, y is equal to 1 upon p, y is equal to 0. So p, y is equal to 1 upon 1 minus p, y is equal to 1. So why 1 minus p? Because the probabilities of all the events, if we do the summation of probabilities of all events, it is 1. So py is equal to 1, the probability that the event of interest occurs. For example, the probability that the customer buys a product or that the patient has a certain disease. This is also referred to as the probability of success. Py is equal to 0. The probability that the event does not occur, the probability of the opposite outcome or the probability of failure. It is equal to 1 minus py is equal to 1. Since the total probability for all possible outcomes must sum to 1, so we can safely write this. Now make sure that the probabilities which we get by this equation depends on what we code as 1, what we are coding as 1. So if death is coded as 1, we will get the probabilities for the death. If we are coding y is equal to 1 for a particular disease, so we'll get the probabilities of occurrence of the disease. So make sure what you are coding it as, what you are coding y is equal to 1. Now let's consider the another example. The odds of winning a game where the probability of winning is 0.8. So probability of winning is 0.8. Probability of not winning is 1 minus p, 0.2. What will be my odds? P divided by 1 minus p. Success divided by failure. 0.8, 0.2, 4. This means that the odds of winning are 4 to 1. For every 4 times you win, you would expect to lose 1 time. Now, if we are given odds, then how to calculate the probability? So, let's say that the odds of the student passing an exam are 2 to the 1. So, odds is 2. Calculate the probability. Odds upon 1 plus odds, 2, 1 plus 2, 2 by 3. So, it's 0.667. Then this means that the probability of passing the exam is approximately 0.667, 66.7%. What is the odds ratio? Odds ratio is a measure used to compare the odds of an outcome occurring in one group relative to another group. It's commonly used in statistics, especially in logistic regression and case control studies, to assess the strength of the association between the exposure and the outcome. Let's understand the odds ratio according to the groups. If you have two groups, group 1 and group 2, and you want to compare the odds of an outcome between these groups, calculate the odds in each group. So odds in group 1, odds 1 is equal to P1 upon 1 minus P1. The probability of success in group 1 upon probability of the failure in group 1, where P1 is the probability of the outcome occurring in group 1. Similarly, odds in group 2 is odds 2 is equal to P2 upon 1 minus P2, where P2 is the probability of the outcome occurring in group 2. Calculate the odds ratio. Odds ratio is equal to odds 1 upon odds 2. So P1 upon 1 minus P1 divided by P2 upon 1 minus P2. Now we are having two groups. Group 1, smokers. Group 2, non-smokers. Group 1, probability of having a disease P1 is equal to 0.3. Here it is 0.1. So what will be the odds in group 1? P1 upon 1 minus P1. So 0.3 upon 1 minus 0.3. 0.3 divided by 0.7, 0.429. So probability of having a disease in the group of smokers. So this is the odds of it. Odds for non-smokers. P2 upon 1 minus P2, 0.1 upon 1 minus 0.1, 0.1 divided by 0.9, so 0.111. Now what will be my odds ratio? Odds of group 1, odds of group 2, so 0.429, 0.111, so this is 3.87. What this figure will interpret? Let's see. Odds ratio greater than 1. It indicates that the outcome is more likely to occur in group 1 in compared to group 2. So in this case, smokers are approximately 3.87 times more likely to have the disease compared to non-smokers. If odds ratio is less than 1, this indicates that the outcome is less likely to occur in group 1 compared to group 2. If this is less than 1. If it is equal to 1, this indicates that the odds of outcome are same in both the groups. Now we are having odds ratio 3.87. Can we calculate the beta coefficient? Yes, it is very simple. Beta is equal to ln OR. Now substitute the value of OR. So beta is equal to ln 3.87, which is equivalent to 1.35. So the logistic regression coefficient beta 1 for being a smoker is approximately 1.35. Now let's make the equation. Our equation is, our logit equation is logit P is equal to beta 0, the intercept, plus beta 1 into the smoker. As a person is a smoker or a not smoker. If the person is a smoker, the value will be 1. For non-smoker, the value will become 0. Beta 1 is 1.35, which we have already calculated. Let's say the intercept value is minus 2. Just we are assuming that its value is minus 2. So what will be my equation? Logit P is equal to minus 2 plus 1.35 into the smoker. So if I want to calculate the probabilities, how can I calculate? It's so simple from where we have started. This one. P is equal to 1 upon 1 plus e raised to minus z. This equation, we will use it. So you can see the same equation we have used. So logit P is equal to minus 2 plus 1.35 into 1. Why 1? We start the calculation for the smokers. So if a person is a smoker, equal to 1, we will insert the value 1. So minus 2 plus 1.35 equal to minus 0.65, which means that if we calculate P with the help of this formula, see this and this both are same thing, we get P 0.343. So the probability of having the health condition for a smoker is approximately 34.3%. So the probability turns out to be 0.343 of having the health condition for a smoker is approximately 34.3%. For non-smoker, what we will do? We will insert this value as 0. Just here. In first case, we inserted 1 and in second case 0. So now we are only left out with minus 2. So P is equal to 0.119. So the probability of having the health condition for a non-smoker is approximately 11.9%. These are the probability calculations. This model allows to estimate the probability of having the health condition based on smoking status. Now, how we will do the interpretation based on the coefficient? See, there are 5 scenarios: 0.20, 0.50, 1, 1.5 and 1.7. We will subtract 1 from this. So e raised to beta minus 1. We will subtract 1 from this. Why we are subtracting 1? Subtracting 1 from the odds ratio helps to interpret as a relative change in the odds. The subtraction gives us a clear percentage change interpretation. So if odds ratio E beta is greater than 1, the outcome is more likely, and E beta minus 1 gives a percentage increase in the odds. So if we take minus 1, it will give the percentage increase. If E beta is less than 1, if that is the odds ratio, E beta is less than 1, the outcome is less likely, and E beta minus 1 gives a percentage decrease in the odds. So minus 1, it will be minus 0.80, minus 1, minus point, it will be minus 0.5, 0, 0.5, 0.70. The percentage change in odds, so what this will be? If I convert it into the percentage, minus 80%, minus 50%, decrease in odds ratio. This will be increase in odds ratio, 50% and 70%. Let's say that the logistic regression coefficient beta is 0.5. So odds ratio will be e raised to 0.5, which is 1.65. Now deduct minus 1 from this. Deduct minus 1 from this. What I will get? This means that the odds of the outcome increases by 65% when the predictor increases by 1 unit. Since 1.65 minus 1 is 0.65, which is a 65% increase. Now decrease in odds ratio. Let's say beta is 0.5. Beta is having a negative value. So OR is equal to e raised to minus 0.4, which is 0.67. This means that the odds of the outcome decreases by 33%. See, E is a exponential constant. Its value is fixed. So this means that the odds of outcome decreases by 33% when the predictor increases by 1 unit. Why it decreases? Because this is minus 1. How much it will decrease? 33% decrease will be there when the predictor increases by 1 unit. Now let's download one data set. So for this we will go in Kaggle, click here. And right here, just a minute, right here, GRE, GPA, admission data we want. So you can download this data set. Name of the data set is graduate admission. It contains the GRE, GPA scores and the rank of the institute. Just press download and the data will be downloaded. Now you go in STATA, file, import, CSV file, click here and click on this admissions, open. So now we are having the columns such as admitted, the student is admitted. If yes, then indicated by 1. If no, indicated by 0, 0. GRE score, GPA score, rank of the institute, the undergraduate institute. Click submit. Now run the command browse. So you will be able to see the entire data frame, admit, GRE, GPA, rank. Admit. This is our dependent variable and it is categorical. See, 0 and 1. 0 and 1. We want to find out that is GRE significantly affecting the score of GRE, significantly affecting the admission, score of GPA, affecting the admission, and the rank of the undergraduate affecting the admission or not. Now close this and we will see the research question. What is our research question? A researcher is interested in how variables such as GRE, GPA, and prestige of the undergraduate institution affect admission into the graduate school. The response variable admit, don't admit is a binary variable. So the admission status 1 is admit, 0 is deny. GRE, GPA is continuous predictors. Rank is a prestige of the undergraduate institution, 1 to 4 category. Research question: do GRE score, GPA, and the undergraduate institution's rank significantly predict admission into the graduate school? Hypothesis: null. GRE, GPA, and rank do not affect the admission likelihood. That is, a beta is 0. Alternative: at least one predictor significantly affects admission likelihood. So first we will see the descriptive statistics, and for this we will run the command tab rank. So how many students have taken the admission from rank 1 undergraduate colleges, rank 2, rank 3, rank 4. So how many students have applied, not got the admission, still they have not got the admission. How many students have applied? So 1, 2, 3 and 4, total 400 students are there, and in this some have got the admission and some have not got the admission. This is still the application we have got it. Now how many got the admission? So for this we'll be running tab admit. So out of 400, 127 got the admission. So let's do the interpretation. The data reveals that among the 400 students, 15.25 were from universities which rank 1, while 37.75% were from rank 2. In addition, 30.25 students belong to rank 3 universities, and 16.75 came from rank 4 universities. So this is basically the application which we have received. How many got admitted? Only 31.75%, that is total 127 individuals got the admission. Now we have to see that what are the factors which are influencing, or rather does GRE, GPA, the rank of the institutions affect the admission or not. So now we will run the logistic regression. So for this we will go in STATA logit. What is our dependent variable? Admit. Based on what? GRE, GPA. Now rank is of the institute and it is a categorical 1, 2, 3, 4. So use I dot rank. This will convert it into the dummies. Enter. I'll explain this concept. We got the results: GRE, GPA, rank 2, rank 3 and rank 4. The result will not be generated for rank 1 institute as it is a baseline which will be captured from the constant. Please remember, the number of dummies will be equivalent to the number of labels minus 1. I have already explained this concept in my linear regression categorical variables. Please refer that video. Now let's do the interpretation of this output. The logistic regression model examining the likelihood of admission based on GRE, GPA and undergraduate institution rank was statistically significant overall. See this value 41.46 and this value is less than 0.05. This means that the model is significant, indicating that the predictors jointly contribute to explaining admission outcomes. The pseudo R-square, this one pseudo R-square, value is 0.0829, suggests that approximately 8.3% of the variance in admission can be explained by the model. See here R-square is less, but we don't emphasize on R-square in logistic regression. Rather we give more importance to the model fit and the classification table. Now we will do the interpretation of GRE and GPA scores. GRE scores were found to have a small, see this value 0.022, but statistically significant positive effect. Why? Because this p value is less than 0.05, meaning that for each 1 point increase in GRE, the odds of admission increase by about 0.26%. Similarly, GPA showed a strong positive association with admission because beta is 0.804, p value 0.015 less than 0.0, p value 0.015 less than 0.05, indicating that 1 unit increase in GPA is associated with more than 2-fold increase in the odds of admission. In contrast, the rank of the undergraduate institution was negatively related to admission likelihood. See, rank 2 institute, rank 3, rank 4. Compared to applicants from rank 1 institutions, the reference group, those from rank 2, beta is 0.65, rank 3 minus 1.24, and rank 4 minus 1.55, the institutions had significantly lower odds of admission. This implies that the students from the lower ranked institutions face a disadvantage, with the effect becoming more pronounced as rank decreases. Now this coefficient, we want to convert it into the odds ratio. How we can do it? See, odds ratio is equal to e raised to beta. So beta is equal to ln odds ratio. This we had seen previously also. So what we will do, coefficient is 0.0002, 0.002. Odds ratio is, just insert the value e, the beta value, and I will get 1.0022. Similarly, 0.804, e raised to 0.804, I will get the value 2.23. And when it is minus 1.55, I will get the value 0.2119. Now, how to do the interpretation? That also we will see. But can I generate the odds ratio directly in STATA? Recall the previous command by pressing page up and write here OR, odds ratio. And we got the values. These are all odds ratio. So let's do the interpretation. So now the command line is logit admit GRE GPA I.rank comma OR. Looking at the predictors, GRE score had a small, this one, but a significant effect. This means that for every 1 unit increase in GRE, the odds of being admitted increase by about 0.2. How? See, just deduct 1 from it. This we had seen earlier also. Deducting 1. Okay, deducting 1 from odds ratio and then doing the interpretation. So while this effect is modest, it is statistically significant. Now let's talk about GPA. GPA 2.23. What will be the effect? -1. This indicates that for every 1 unit increase in GPA, the odds of admission are more than twice as high, about 123%. -1, 1.23 into 100, so 123%, holding all other variables constant. What about the ranks? What about the institutional ranks? Institutional ranks was also an important predictor. Compared to students from rank 1 institutions, applicants from rank 2 institutions had about 49% lower odds. Why 49? This is 0.50 -1, so it will be 49%. This is 0.509 -1. What about the rank 3? 0.261 -1, so it is 79%. So those from rank 3 institutions had about 74% lower odds, and applicants from rank 4 institutions had about 79% lower odds. So rank 3 74, so it is 1 minus 0.26. Rank 4 1 minus 0.21, so 79. So it's just a small correct. Previously I had I discussed that for rank 3 it is 79. No, 1 minus 0.27, 1 minus 0.26, it is 74%. 1 minus 0.21, it is 79. Thus, the likelihood of admission decreases substantially as the prestige of the undergraduate institution decreases. Can I generate all this using the graphic user interface? Yes, I can do it. I'll go in statistics, binary outcomes, logistic regression, dependent variable, admit, independent variable, it is GRE, GPA. I can directly insert rank, make sure it is prefixed with I.rank, or click on this 3 dots, variables, rank, add to variable list. So I.rank will appear just here, add I.rank will appear automatically. Click OK and just press, just wait, go in the reporting statistics, report estimated coefficients, press submit. So this will give me estimated coefficients equal. If I require odds ratio, again click here, submit, it will give me the odds ratio. Now let's proceed further. We want the margins. Margins, these are predicted probabilities. This shows the likelihood of the event occurring. Example, being admitted for individuals with specific characteristics while holding other variables constant, usually at their mean or median. So we want The margin, the probability is according to the rank of the institutions at means. Let's run this also. So margin rank at means. Got the value? The same thing I can also generate with the help of graphic user interface. Go in statistics, post estimation, click here, marginal means, at sample means, launch, categorical, rank, analysis type, marginal means of outcome for levels of covariate, and just press submit. See this, you got the same value. Just see here, you got the same value. Okay. Now let's do the interpretation for this. The model is predicting the probability of admission for a student with GRE 587.7, GPA 3.389. The table presents the predicted probabilities of admission for students from each college rank holding GRE and GPA constant at their mean values. Rank 1, best college. Predicted probability of admission is 0.5166. How? See this value. So this is the probability. This means that an average student from rank 1 college has about 52% chance of admission, significantly above 0.5. Why we are using the word average? Because it works on means. Rank 2, predicted probability 0.352. Students from rank 2 colleges have a lower probability of admission compared to rank 1, but still fairly good chances. Predicted probability for rank 3, 0.218. Students from rank 3 college faces a much lower chance of admission. 0.218, probability is very less. Rank 4, predicted probability 0.1847. This is the lowest probability among the groups. Students from rank 4 colleges have less than a 1 in 5 chance of admission. So this is a margin. These are the predicted probabilities for the categorical data. What about the continuous? So we will compute for GRE. The command line is start computing for GRE score 200, increment of 100 and stop at 800. 200, increment of 100, 200, 300, 400 and stop at 800. What is the command? Margins, comma, at. Let's run this also. Enter. And we got the values. This we can also generate with the help of graphic user interface. So go in statistics, post estimation, marginal means, at sample means, launch. Now convert this into continuous, activate GRE, and here we will have to write 200 into bracket 100 and 800. Submit. Cancel. Is it the same value? Yes, we got the same values. See this, we got the same values. Okay, let's do the interpretation. The table presents the predicted probability of admission at different fixed GRE scores while holding other variables constant at their mean values. At GRE 200, 1, so we start with the first one. The probability of admission is 0.167. At GRE 300, the probability rises to 0.199. At GRE 400, the probability increases further to 0.234, that is 23.4%. At GRE 500, 27.5%, 600, 31.7%, 700, 36.5%, and at 800, 41.4%. In case of logistic regression, we go for the model fit. So logistic regression is estimated using maximum likelihood estimation. The likelihood function measures how well the model's predicted probability match the actual outcomes. So taking the log likelihood makes it easier to work with. So how we can generate this model fit? Right here, stat I see, enter, and we got the model fit. Now let's do the interpretation. This is LL for model and this is LL null. The fitted model's log likelihood minus 229 is higher, that is less negative, than the null's model log likelihood minus 249. This indicates that including GRE, GPA and rank improves model fit compared to using only the intercept. It means that the model is better than the baseline model. The baseline model consists only of intercept. Now this we can also generate with the help of graphic user interface. So go in statistics, binary outcomes, post estimations, and here is it, goodness of fit. And here the information criteria is there. Just click here and press submit and you will get the same value. Now we will see the goodness of fit. In logistic regression, the goal is to assess how well the model predicts the observed outcome. So goodness of fit test evaluates whether the predicted probabilities from the model match the actual data or not. The null hypothesis is the model fits the data well, no difference between observed and expected. Alternative, the model does not fit well. The command line is stat goodness of fit. And we got the value 0.4467. So what is our interpretation? As a p-value is 0.4467, this value, which is greater than 0.05. We fail to reject null. This means that the model shows no significant lack of fit. The predicted probabilities are consistent with the observed data. This is very good. This is desirable. We can generate the same output with the help of graphic user interface also. Go in statistics, binary outcomes, post estimations, goodness of fit test, and here GOF, and click submit. So we got the value. If we want the Hosmer-Lemez goodness of fit test, click here, submit. So this will be according to the group 10. So we can do the interpretation either from here or from here. Both of them gives us the same value. You can also run the goodness of fit by the command user interface. Just press page up and write group 10. This will activate the Hosmer-Lemez test. Further, now we want the predictive accuracy. So for this, we'll be generating a classification table. Classification table, also called the confusion matrix, is a tool used to evaluate how well a classification model predicts the outcome. It compares the predicted categories of the dependent variable with the actual observed category. See, this is classified according to the model plus and minus, and this is the original values, that is 1 and 0. Okay, 1 and 0, and this is according to the model. We have to see diagonally 30 and 254. These are correctly classified cases. Why? If we talk about classified plus, it means that the student got the admission, and the original values also confirm that the student got the admission, so it is correct. 30. Classified minus, student did not got the admission, and the original values also say the same thing. So 254. So 30 plus 254 are the correctly classified cases. If we talk about 19 and 97, these are misclassified cases. So let's run this command in STATA. It is estat classification, or you simply write estat class and it will give you the results. Now let's do the interpretation. True positives. 30 cases were correctly predicted as admitted. 30. False positive. 19 cases were incorrectly predicted as admitted but actually not admitted. True negatives. 254 cases were correctly predicted as not admitted. 254. Okay, this is correct. True positives and true negatives are desirable. False negatives. 97 cases were predicted as not admitted but were actually admitted. Now we have to also interpret the sensitivity, specificity, positive predictive value, negative predictive value. And for this, we will run one more command, and that is LROC, receiving operating characteristics curve. Okay. So sensitivity, specificity, positive predicted value, negative predicted value. This is our ROC curve, 0.69. The ROC curve is a graphical tool used to evaluate the performance of the classification model like logistic regression, decision tree. It shows how well the model separates two classes, positive versus negative, across different classification thresholds. Sensitivity, this one, it is 23.62%. Only 24% of actual admits were correctly predicted. Model struggles to identify admitted students. Specificity, true negative rate, 93.0%, 93.04%. About 93% of non-admitted cases were correctly predicted. Model is very good at identifying non-admits. Positive predictive value, precision, 61.22%. Among those predicted as admitted, 61% were truly admitted. Negative predicted value, 72.36%. Among those predicted as not admitted, 72% were truly not admitted. Now, whatever output we have generated with the help of command user interface, same thing I can generate from here also. Statistics, post estimation. We have seen for the marginal effects, specification, goodness of fit, launch. So from here, I will get the goodness of fit. Press submit. I got the value. Classification table, submit. I got the values. Information criteria, submit. Got the values. Anything else left out? And summary. The same thing I can get. Sorry, ROC curve is left out. ROC curve, launch. Just press submit and I'll get the ROC curve. Sensitivity, specificity, launch, submit. This is a sensitivity, specificity curves. I can get also the results from binary outcomes, post estimations, and it will give me the same menu. ROC curve, submit. So this was all about logistic regression analysis using STATA. For more videos on STATA, kindly refer to my playlist. I also uploaded many videos on data science, machine learning, and artificial intelligence on my YouTube channel named Dhaval Maheta. To watch the full videos, please subscribe to my YouTube channel and check the playlist. Please don't forget to like and share my videos. You can also follow me on different social medias, link given in the description box.